Students, welcome to part B of today's class. We have been looking at the nuclear reaction kinematics, and this involves the measurement of energy and all these things evolved and absorbed in nuclear reactions. And what we were about to do is that we were about to find the expression for Q value in a certain reaction. In this certain reaction, we have a target nucleus X, and which is at rest, and X is the small x is the incident particle, and Y is the target, not the target but the product nucleus, and small y is the product particle. So this was a reaction which we had represented diagrammatically by the diagram given side below it, and we had looked at m. Small m is the mass, capital M the mass, they are the masses of the particles and the nuclei, and similarly v are the velocities. So we had looked at the conservation, we had looked at the momentum components like this. We have found all the momentum components, and if we write the conservation of momentum along the, so we had written here, by applying conservation of momentum along horizontal direction, so what we have, we can write it as mx vx. We don't have a plus sign here because we don't have a momentum of this, because this is at rest, and then is equal to obviously my vy cos of phi plus, which is this one, plus my vy cos of theta. So this would be our equation, I think 4 or 5. This would be equation number 5. And then we have along the vertical directions, what would be along vertical direction. Along the vertical direction, you can write that as let me find some space. Vertical direction, you see, we have this one, and then we have this one. So they are opposite in direction. So this one. So we can write it like this. We can write my vy sine phi, m capital Y, v capital Y. See, this capital Y stands for the big ones, that is the nucleus, and the small ones, that is the particles. It's small letters. This is equal to, I think I made a mistake out here because this should be, I think, small letter. Yeah, it's okay. It's my vy sine phi, like that, because this my vy sine theta. Okay, so this is there like this, and this is equation number 6. So students, what we can do is we can eliminate phi. How can we eliminate phi? You take this on the right hand side, so we have my vy, and then we also have my vy. So if I take this on the left hand side, and then we take the rest on the right hand side, and you square them, so what do we have? My square vy square cos square phi, and y square vy square sine square phi. So when you add them up, see, sine square phi and cos square phi becomes plus, the sum of this becomes 1, so that what we get is that, so from 5 and 6. I'm sure you can do this part of the calculation. What do we have? We have my vy is equal to mx square vx square, because we have this one. But then again, when you square this, we have plus my square vy square minus twice mx. So because we will have a square term out there, this is mx my. Let me rub this. We have mx my and mx my vx vy, of course, vx vy, because you see, when I take this on this side, then we will have, or if I keep it this way, this will be mx vx minus this one. So you see, we have mx vx square, which I have written here. Then we'll have this square, which would be like this, cos square theta, which will combine with this one. And then what we'll have? We will have this plus, plus b. This is the equation number 7. This is equation number 7. And then we have to proceed further. And for proceeding further, what we do is, we assume here that, we don't assume here, we know that what is Ex. Ex, look at X. X stands for the small particle, that is the incident particle. And what E stands for? E stands for the kinetic energy of that small particle. So this is equal to half mv square. So it is mx into vx squared. Okay. And what about this one? This doesn't have a kinetic energy because it is at rest. What about this one? This is the big nucleus Y. So this would be E capital Y, and this is equal to half into m of y into vy squared, like this. This is capital Y. And then for this small particle, what would we write? Kinetic energy is, we would have E. See, all the E's are capital, even though we have the suffixes and the masses and the velocities in small letters for the small particles and capital letters for the nucleus. So now we are moving to this one. So this is, so here only these, all these are moving, that's why. So we have a moving here and a moving here and a moving here. So these have kinetic energy. So we have E small y now is equal to half into m small y into v small y squared. So you see, this one, and this one. Now see students, we have here what? We have here in this expression, everywhere we have a product between mass and, sorry, this should have been Vy. Very sorry here. So we have a mv squared. Yeah, we have a mv. Here what we have? We have mv square. We have mv square. We have here mv square and here mv. So we will take the mv from here, and when we do that, what will we get here? So let me clean my board. We have, just look at a general term, E is equal to half m v square, which gives twice E is equal to m v square. So that that implies twice me is equal to m square v square, and so what would be root over twice me? Root over twice me would be equal to mv. So wherever we get mv, we write root under root twice me in the expression that we had in the equation that we had done, that we had seen just now, that we had written just now. So we will do that, and then we will see how the expression changes. We'll see. And talking about the equation that we did by applying the conservation of momentum and after eliminating the phi. So our expression becomes like this. We had my vy square. We had square on both the terms, both the factors. Then we had mx square vx square plus twice. I think I made a mistake in my last equation. Maybe I forgot to put the square out here. Please do the correction. My square vy square minus twice mx my vx vy cos of theta. We had that. I don't know whether I had written it correctly, so please do the correction. This was the exact equation that we did after eliminating phi. Now using the substitution form mv in terms of energy, this can be written as twice twice my out here, which is equal to twice ex mx plus twice my minus 4 mx. The 4 comes because of this one. 4 mx my ex ey under root, and this is cos theta. And this not substituting, so we have still one more step. So ey then gives us what? See, we have 2 all over, so you see 2 will be cancelled, and with left will be left only a 2 here out here. So we have here, this is ex, so 2 will be, all the 2's will go this way, and we will have a 2 out here. Ex mx divided by my, m capital Y. So please be careful with the capital letters and small letters, because it might lead to giving you a erroneous result at the end if you confuse them like I do. So my minus 2 by my mx my ex ey half cos theta. So this is like this, and substituting this in equation number 3. What was equation number 3? Equation number 3 was q is equal to ey plus e capital Y minus e small x. So we give this value there, and we arrive at the expression for q value. So we'll do in the part C of our class, and we'll do the rest, that is proton induced reaction.